Fundamental physics is currently defined by a persistent tension, the mathematical incompatibility between the continuous and the discrete. General relativity describes gravity through the deterministic curvature of a smooth spacetime manifold. Quantum field theory, however, treats the universe as a series of discrete, quantized excitations within probability fields. A century of theoretical effort has yet to yield a consensus model that successfully welds microscopic discrete space to macroscopic geometric determinism. Most bottom-up approaches, like string theory or loop quantum gravity, rely on the existence of unobservable building blocks at the smallest scales. Unifying these pillars requires addressing the foundational assumption that reality is built from the bottom up, rather than being constrained from the top down. The Psi-Phi Theta theory of infinity offers an alternative, a universe carved out of an infinite mathematical continuum. In this model, structure is determined by specific boundary conditions and identities. These boundary equations act as filters, selecting specific coordinates across different modalities, from algebraic polynomials to trigonometric phase angles. For a mathematical entity to manifest as physical structure, it must satisfy these conditions with zero residual error. This constraint mechanism is observable in a specific derivation known as the Euler Swoosh. This function, s of x equals x plus 3 divided by 2, acts as a linear boundary. The numerator uses the integer 3 as a discrete translational operator. The denominator applies a division by 2, which functions as a standard scale reduction. We can test the stability of this discrete boundary by seeding it with a continuous parameter, Euler's constant e divided by 4. Calculating the output for this input results in a scalar value of approximately 1.839785. This maneuver attempts to align a parameter of natural exponential growth with a rigid algebraic ledger. In pure algebra, the Tribonacci constant is the real root of the cubic equation z cubed minus z squared minus z minus 1, or roughly 1.839286. When we compare the output of our function to this exact polynomial root, the two values sit in close proximity. There is a discrepancy between them of roughly 4.98 times 10 to the negative fourth. Within this framework, numerical proximity does not constitute an identity. Because the residual is non-zero, these two values cannot be mathematically unified. This gap is defined as a residual shadow, a footprint left by a continuous parameter that failed to resolve within a discrete matrix. To find a more stable intersection, the framework introduces a second constraint, the hyperbolic reciprocal function, 5 divided by z. This second curve represents a spatial inversion, where large values are compressed and small values are expanded. We can force an agreement between these two geometries by requiring the original linear function and the hyperbolic curve to intersect at a single coordinate. To find that coordinate, we scale the linear input to z over 4 and set the equations equal to one another. This creates a collision between a linear translation and a nonlinear spatial folding, resulting in a specific geometric anchor. This leaves us with a single boundary condition to solve. The quantity z over 4 plus 3 divided by 2 equals 5 over z. Clearing the internal fraction simplifies the left side of the equation to z plus 12 divided by 8. By cross-multiplying, we eliminate the denominators and move the system out of the rational modality. This results in a quadratic equation, z squared plus 12z minus 40 equals 0. The interaction between two continuous curves has collapsed into a single, rigid polynomial boundary. Solving this quadratic equation allows us to derive a precise root for this geometric proxy. The positive solution is the square root of 76 minus 6, which is approximately 2.717797. Forcing these geometries to agree has stripped away their independent degrees of freedom, producing a highly constrained algebraic surrogate. This algebraic root, derived from a geometric collision, sits very close to the transcendental constant e. This sequence shows a dimensional inversion, where separate continuous geometries are forced into an algebraic agreement. The system cannot derive a pure transcendental number from a closed algebraic intersection. The gap remains. With no identity to bridge that microscopic difference, the root z plus remains a separate, approximate entity. This is the shadow principle. The continuous world of E leaves a measurable geometric print inside the discrete ledger, even if they never truly touch. This residual shadow is distinct from cases where a solution cannot be found on the real number line at all. When an equation cannot be resolved on the real axis, the mathematical tension is displaced into the complex plane. These unresolvable tensions form branch shadows, such as those that sit permanently at positive and negative I on the imaginary axis. Dimensional inversion moves this geometric information between the real axis and these complex depths. The number system acts as a reactive network, linking values through these rigid geometric constraints. The 0.0004 gap we observed suggests a universe where exact symmetries collapse into physical structure, while remaining mathematical tensions are preserved as permanent geometric shadows.